All right, yeah, so as you mentioned, I'm a postdoc at NC State, and I'm going to talk about little things. So imagine that you wanted to help everyone on the entire globe. It'd be kind of difficult to do. Well, what could you do? If you had superpowers, maybe you could do that, fly around in a split second, be super strong, lift buildings off of people, that sort of thing. Well, if you don't have superhuman powers, you're going to have to find a different way to help everyone. Okay, so that's where my story begins. And to think about how we can do that, let's first think about a substance, a material that everyone is very comfortable with, familiar with, water. Water falls from the skies, it's in our lakes, in our bodies, we drink it. Okay, so is there anything special about water? What is water? Well, first of all, can anyone tell me the chemical abbreviation for water? H2O, right. It's the most well-known chemical abbreviation there is. I am not a chemist, but I knew that. And so why do we call it that? Well, because water is made up of a bunch of particles called atoms, and there are 3 of them in each molecule, 2 of them being hydrogen, 1 of them being oxygen. And this is basically how they're located relative to one another. Now, why this is important is because we can learn everything about a material based on which atoms are connected like Lego pieces together to make that material, and also how they're located relative to one another, how far apart they are, what angles they are next to one another. And so this is the standard location of where these atoms are in a material. But if you, say, move the oxygen atom a little bit, perhaps now we can kind of change the properties of that material, how durable it is, maybe how well it conducts electricity. Okay, so this is one molecule. Now, of course, in water there are lots of molecules, and they are all stacked up next to one another. So not only is it how one atom is located next to the other in a molecule, there's also patterns of these molecules throughout the material and how they're located relative to one another. And so this pattern might result in some properties, and this pattern might result in different properties. Okay, great. So we understand that with a material, if we know the atoms, if we know where they're located, we can understand the material better. Okay, so how are we going to measure where all these atoms are located? This becomes a problem. So to get at this idea, let's first think about a penny. Now think about the width of a penny, right? Really small. It's about 1 millimeter. So let's zoom in on 1 millimeter. Let's imagine this whole screen here is 1 millimeter. Okay, now we need to zoom in 1,000 times more. And now we're into a micrometer. So imagine how small that is. Now zoom in another 1,000. And now we're into a nanometer. And right there is our water molecule. That's how big it is. And so when we're talking about atoms, this is the scale that we're working on. Tiny little particles that are way too small for us to see, too small to measure. So if we want to learn about materials, how are we going to do it without one amazing ruler? You can't just stick a school ruler up to these atoms and measure where they're located, right? So we're going to need a really fancy ruler. And so here is our fancy ruler. It's called the spallation neutron source, and here's a little video basically describing how the data is collected. The thing to note is that this is a big collection of buildings, and all these buildings in unison are our ruler. So there's no sound, but that's okay. Basically what it's saying is that at this spallation neutron source, you can learn about materials that end up helping all these different areas: medicine, electronics, cars, airplanes. And so this is what's underneath the buildings. Big, fancy material. It's sending signals from across the country that go in here, and they basically collect a bunch of protons and send it through here, accelerate it, and then spit it at a substance. What's known as spallate. It shoots off neutrons in different directions, and what you end up with is a pattern. So in essence, to kind of summarize, and excuse me if I'm not a material scientist, but What it is basically putting a strobe light into a material and getting out a pattern. And this is the pattern. So now we wanted to know where all these atoms are located. This doesn't really show us that. It's a nice picture, but I don't see any atoms there. Fortunately, we can use some nice mathematics, some functions, and from this pattern, we can get at where we believe the atoms to be located, which is great. The problem is that this pattern can also produce that set of atoms. And they both match that pattern. Okay, well, what we're trying to do here is we're trying to understand these materials to improve them. That's how we're going to basically help everyone. Okay, so one example in terms of improving materials is, say we want to improve batteries. We all probably are familiar with batteries. A lot of us have cell phones. If you have a smartphone like I do that needs to be charged twice a day, it's pretty annoying. The first pattern could result in a battery that's wonderful, lasts forever, you get to have conversations with your friends, and the second pattern, not so much. And so we need to understand not only where these atoms are located, but we also need to understand how confident are we in where those atoms are located, since there's some uncertainty here. And that's really where I come in. I didn't say this in the introduction, but I work in the statistics department, and so my job is to take the science and quantify the uncertainty, give confidence in our estimates. And so here we have estimates of where the atoms are and basically clouds of possible locations for these atoms that are also fairly likely. And in doing so, we can help the world. We can improve materials and technologies by understanding materials, and we understand materials by using statistics. Thank you.